am Dan Gowde, Assistant Professor in Mathematics, Center for Distance Education, Shivaji University, Kolhapur. Today I will discuss the nilpotent group from the group theory of algebra, MSc first, semester first. The nilpotent group, definition of nilpotent group. A group G is said to be nilpotent if ZM of G is equal to G for some m. The smallest such that ZM of G is equal to G is called the class of nilpotency of G. Every abelian group is a nilpotent. Relation between a nilpotent and abelian group. Every abelian group is a nilpotent, but nilpotent group is not a abelian group. That is, if G is abelian, then Z1 of G is equal to Z of G, hence G is a nilpotent. Now next theorem, subgroup of nilpotent group is nilpotent. Prove that subgroup of nilpotent group is a nilpotent. For proof, suppose that G be a nilpotent group, hence there exists a positive integer m such that ZM of G is equal to G. Suppose that H is a subgroup of G. We have to prove that H is nilpotent. Therefore, when H is equal to singleton E or H is equal to G, then the result is really true, that is H is a nilpotent group. Now let's suppose that singleton E is a subgroup of H is subgroup of G. Therefore, there exists X belongs to H intersection Z of G, such that Gx is equal to Xg for all G belongs to G. Will imply that Hx is equal to X into H for all H belongs to H. Hence, X belongs to Z of H. Thus, H intersection Z of H is subset of Z of H. Therefore, as Z of G is equal to Z1 of G and Z of H is normal subgroup of H, we get H intersection Z of G is a subgroup of Z1 of H. Now suppose that X belongs to H intersection Z1 of H, Z1 of G. Therefore, X belongs to Z2 of G will imply that X multiply Y multiply X inverse multiply Y inverse belongs to Z1 of G. But X inverse Y inverse belongs to Z1 of G as X belongs to H and Y belongs to JH. We get X inverse Y inverse belongs to Z inverse Z1 of G. But this implies that the X belongs to Z2 of H. This shows that H intersection Z2 of H is a subgroup of Z2 of H, and continuing in this way, H intersection Zn of G is a subgroup, is a subset of Zn of H, and hence particularly H intersection Zm of G is a subgroup of is subset of Zm of H, and H intersection G is subset of Zm of H, and H intersection H is subset of Zm of H, but it is always Zm of H is subset of H, and we get Zm of H is equal to H, and hence this proves that H is nilpotent group. H is nilpotent group. We have already proved that singleton E is equal to H is equal to G, then H is nilpotent, and in this case we also proved that H is nilpotent. Next one theorem, homomorphic image of a nilpotent group. Prove that every homomorphic image of a nilpotent group is a nilpotent. Now suppose that G is a nilpotent, and define a mapping phi from G to G1 be an onto homomorphism we have to prove that G1 is nilpotent. We have to prove that G1 is nilpotent. As G is nilpotent, there exists a positive integer m such that Zm of G is equal to G. Now Z of G is equal to x belongs to G such that xg is equal to gx for all G belongs to G. Z of G1 is equal to x belongs to G1 such that xg is equal to gx for all G belongs to G1 is equal to phi of x belongs to G1 such that phi of x into phi of G is equal to phi of G into phi of x for all phi of G belongs to G1. But this shows that phi of Z of G is a subset of Z of G1. Now suppose that x belongs to Z2 of G and x inverse y inverse belongs to Z1 of G. Therefore, phi inverse of phi of x inverse y inverse belongs to phi of Z1 of G. Therefore, phi of x, phi of y into phi of x inverse, phi of y inverse belongs to phi of Z1 of G. This shows that phi of x belongs to Z2 of G1 and this x belongs to Z2 of G and this is phi of x belongs to Z2 of G1. Therefore, phi of Z2 of G is subset of Z2 of G1 and continuing in this way for all n, phi of Z1 of G is subset of Z1 of G1 and hence particular phi of Zm of G is subset of Zm of G1 and hence phi of G is subset of Zm of G1. But phi is onto, therefore phi of G is equal to G1. Therefore G1 is subset of phi of Zm of G1 is subset of G1. Therefore Zm of G1 is equal to G1 and hence which proved that G1 is nilpotent, which is homomorphic image of G and homomorphic image of nilpotent group is a nilpotent group. Next one theorem, any group of order p raised to n is nilpotent or any p group is nilpotent. For proof, suppose that G is a subgroup, G is a group and with the cardinality of G is equal to p raised to n. We have to prove that G is nilpotent. If G is equal to Z of G, then the result is trivial. Assume that G is not equal to Z of G, then P divides order cardinality of G and we get Z of G is not equal to singleton E and hence cardinality of Z of G is not equal to 1. Further, cardinality of Z of G divides the cardinality of G as Z of G is subgroup of G. We have cardinality of Z of G is equal to p raised to r for some r less than n. Then cardinality of G divides Z of G is equal to cardinality of G divides cardinality of Z of G is equal to p raised to n minus r, which implies that p divides cardinality of G divides cardinality of Z of G and this is Z of G divides Z of G is not trivial. Therefore, Z of G divides Z of G G divides Z of G is not equal to Z of G. Therefore, by definition of Z2 of G, Z of G is subset of Z2 of G and hence cardinality of Z1 of G is less than cardinality of Z2 of G. Continuing in this way, we get Z1 of G is less than Z2 of G is less than less than cardinality of G is equal to p raised to m. Hence, there must exist some positive integer m such that cardinality of Zm of G is equal to p raised to n. This shows that G is nilpotent. G is nilpotent.